Time to get started. We have an assignment due Wednesday. We have a project now due in a couple of weeks, 2.5 weeks, something like this. If you missed Friday, I think just about everybody was here on Friday, but if you missed Friday, we did something very important for that project. I also will not have any afternoon availability today, unfortunately, but I will have some both tomorrow and Wednesday. Any questions before we dive into new fun topic? Okay. Question.
Might be just good to get from the sales stuff.
That is a great question. Last I heard from the TA, he said early next week. It is currently early next week, so I would anticipate any day now. He sent me his task list and progress. He made a lot of progress on things last week, but there was still quite a bit to go. So hoping, I know it's been over a week now, and I try to really have that week turnaround when I can. So, should be soon. All right, we've talked about context-free grammars. We've talked about what we can do with context-free grammars. We did CYK and the membership problem, which was a really thrilling experience, I'm sure. But we're going to transition from that now down into the state machine representation of context-free languages. So we'll start with that. Just like with regular languages, we have multiple different ways that we can represent context-free languages. We talked about the grammars, but now it is time to represent them in terms of a state machine. The reason we didn't start with state machines here is they're a little bit more complicated than they were in the regular language land. So let's take a second and refresh ourselves on the difference between a regular language and a context-free language. What do we think? What were the differences between these language classes? What was the restriction on a regular language? And maybe now that we've seen context-free grammars, how has that restriction been relaxed when we look at context-free languages?
It's just allowing terminals on the other side.
Yeah, so for grammars, we had to have a linear grammar for regular languages, and now for context-free, you can have that non-terminal or multiple non-terminals anywhere in the string. What does that do? What is that the equivalent of? What does that make you think of? How much power does that actually give us? Remember that the restriction on regular languages was that we needed a finite amount of memory. The states in a DFA or NFA were finite, and that meant that even for an infinite number of strings, there needed to be some kind of repetition that allowed us to be able to produce those infinite strings via some finite amount of memory and looping. So thinking about context-free grammars, what does this mean? Is there a limit to the amount of memory that we are using? If so, how would we define that? So we can recurse in the middle of something. It should make you think of something programmatic.
Stack.
The call stack, yeah. When we are in the middle of a sequence of instructions, we can, at some point in the middle, jump to some other place and execute some other code. Is there a limit to the number of times we can do that? There actually is, but it's a hardware-based limitation. depending on the amount of cache that we actually have. We can do this in modern machines 40 to 50 times before we have a stack overflow. Luckily, in the world of theory, we don't have such limitations. So we will see that context-free grammars, and by association, the state machine representations of it, we allow for an infinite amount of memory, which is really cool. But we restrict the form of that memory to be in the form of a stack. So we can't utilize memory in an arbitrary manner. It has to be in, basically, we're going to use an infinitely sized stack as our memory. So we need extra memory. And we found that there, in fact, really is not a limit to the amount of memory needed. To visualize this, let's take a look at the language a to the n, b to the n. We know this is not regular. We've determined that it is context-free. We've written a grammar for it. But to easily see whether there is a restriction to the amount of memory that we are using, is there a maximum number of a's that come before the b's? Is there a limit to the size of n in recognizing this language in terms of a context-free grammar? By the same recursive definition, we have no limit to the number of a's that can come before the b's. First of all, what was the grammar for this? What grammar recognizes a to the n, b to the n? Something like that. So with a single recursive definition, being able to recurse in the middle instead of just at the beginning or just at the end, we can now place no limit on the number of a's that come before b's. The question is just how many times do we repeat this ASB, and each one adds an extra a at the beginning and an extra b at the end. But we can do this an arbitrary number of times without limit. So how much memory do we need to be able to accept or reject all strings in the language? The answer is infinite. But we can represent a way of, if we had more memory, we can still use this idea of recursing in the middle. And the limitation is now a hardware-based limitation and not a conceptual limitation. So we like to differentiate that in theoretical classes, because as technology gets better and better, the question is, what is the limit to what we can accomplish? If it's a hardware-based limitation, then maybe that means that there's reason to explore more efficient hardware, more capable hardware, because there is something we could do if we had better hardware. So let's actually talk about now a more visual representation of the same class of language that we have grammars for. So we will call them PDAs, push-down automata, and in fact, we'll start with non-deterministic push-down automata, NPDAs. So it works exactly like an NFA, with the exception that we have an infinite stack that we drag along with us as our storage. We have an extra piece of information to define because there's no guarantee that the stack's language is the same language as our input language. We can define a separate language for this stack than we have for the input. And this becomes necessary or useful when we want to store ideas, kind of like variables on the stack. We want the ability to have an abstract representation of the terminal symbols that we see. We'll see how that is useful. So the formal definition of an NPDA, non-deterministic push-down automata, acceptor, I don't care. My joke usually is PDA stands for public displays of automata. So just like before, the only thing that changes is our transition function and the set of symbols that we're going to call the stack alphabet. So we have our same input alphabet as we have before, but now we also have a stack alphabet. Then we need to change our transition function because to transition from one state to another, instead of just reading something from the input and basing our transition on that, we're going to be looking at tuples. We're going to be looking at the character that we're reading in the input and the symbol that is on top of the stack. And that tuple of information will dictate where we transition. Since this is non-deterministic, there may be multiple places to transition, and we have to deal with that ambiguity. So, like we had before, this was our very basic view of an automata. We have the input file, we have the control unit, which are the states and the associated transitions, but now we also carry with it some memory. But the memory is limited to be a stack. Must have a stack, but the stack is infinite in size, meaning that there are no bounds to how much we can store on the stack. Any questions definitionally on what this thing is? Obviously, we need to see some examples of it to see it in action. Okay. So how do the transition function, how does that change? So as I've already spoiled, rather than doing what we did before, just transitioning on the input, we need to transition on something based on the top of the stack symbol. Allowed operations, push pop, and no op, meaning no operation, meaning we don't push or pop. And if the stack is empty, then we can't do anything unless that operation is a push. Although we will kind of define a bottom of stack character for the moment, where if we get rid of the bottom of stack character, then we can't do anything. So the bottom of stack character says the stack is empty. If we remove it, then there's nothing we can do. So range of the transition function must be finite. That means that there's a finite number of stack symbols that we could read, meaning that there are a finite number of tuples. So subset of possible strings pushed to or pop from the stack must be finite. And this allows us to have a finite representation of an infinite number of strings, just like we had with our context-free grammar. With the A to the N, B to the N, there are an infinite number of strings that can be accepted by that within a finite number of rules. So it represents the exact same class, where instead of the looping that we had before with regular languages, we are now going to base this off of recursion, but it's very much like the call stack kinds of recursion, where you're calling a method and you're changing scope. So I find that to be a very useful concept to carry with us as we do this. So here's an example of a transition. It looks a lot more complicated than it did last time. There's a lot more information here. Let's break it down. This says we can transition from state Q1. We are going to pop an A from the stack, push a B onto the stack, and as we do all of that, pop the A and push the B in its place. So it's replacing an A with a B. We are going to move to, sorry, this is read. I'm so sorry. So let's actually label this. This is the from state. We are going to, this is the character we're reading. This is our pop. This is our to state, and this is our push. And since it's non-deterministic on the same outgoing transition, we can have multiple possible incoming transitions. So this is also a to and a push. we must state each one of these on each possible transition. So this would be the equivalent of, in our old NFA, we have some state Q1, and from that we have two different transitions, one of which goes to Q2 and one of which goes to Q3. However, there is now much more information. We can make either of these transitions on an A, but we need to make some stack operations as we do it. We're going to pop a B off the stack. We can only make either of these transitions if our stack has a B on the top of it. And we're going to pop that B in order to make this transition. Think of it like the fee for leaving the state. And then the push is what we acquire when we enter the new state. So there are tolls both at where we leave and where we enter. So we're going to pop the B, and if we take this transition, we're going to replace it with a CD. And this should actually be done from right to left, so that the string that we read here is what's available to you from top down. So this is a D followed by a C. So that's what would replace the B on the stack. So this is how we read this in this notation, but usually that's not what we actually write on the NPDA. We need to write a triple of information, 3 pieces of information. There's the character that we're going to read, there's the associated pop, and there's the associated push. So here we would have the pop. The pop is still a B, and the push is now a lambda. This is saying that the entirety of this transition is popping the B, and this transition is replacing a B with a CD. So lots of notation. Before I erase that, any questions on the notation? We'll give you further examples, I think. All right, here's an example. Here's an NPDA with associated transitions, and let's take a look at what this does. So just like in an NFA, we don't always specify transitions, and if there are no associated transitions, then we just immediately fail. But let's take a second and see if we can figure out what this does. So my recommendation is drawing this out. You're going to have a from state, you're going to have a to state, you're going to have an input character, and you're going to have a pop, and you're going to have a push. And that is guaranteed to be the order that we have in a transition. So we still name our states very similarly, but edges now have 3 pieces of information representing input character read, what is popped from the stack, what is pushed to the stack. And some of those may be empty. So it's not a pop or a push. There is both a pop and a push. And if one of those is empty, then all we're doing is popping. But we can do both in a single transition. We can replace a character with another character. We do know that the pop, though, is always a single character. The push can be multiple characters. So when we see something like the destination we get to having multiple characters, it's okay to push multiple characters. But since we can't dig down multiple characters in the stack, we can only look at the top of the stack. We have to break that apart into 2 different state transitions where we look at each top of the stack character in sequence. So let's figure out what this does. Take a few minutes, see if you can figure out the purpose of this NPDA. What is it doing? little small to read, sorry. Had to fit it all on. Anything we notice about these productions in general? When we're defining these transitions, for instance, what happens when we read an A? We're doing the same thing whenever we read an A. What is that?
A one is pushed or popped from the stack, and then 2 ones are pushed to the stack.
That's true here. So this character that was on the stack stays on the stack, and then we are adding something to the stack. And here, what was on the stack is kept on the stack. So we're popping and pushing the same character. Pop here, since we push from right to left, we're pushing back the character that we just saw, and then we're pushing another character. Guess I should draw the same arrow that I used before. But that character is always the same thing. It's always a 1. So when we read an A, we are adding a 1 to the stack. What do we do when we see a B? Yeah, there has to be a 1 on the stack. And we are popping it. Interesting. What does that tell us about what this is doing?
It's adding an equal number of A's and B's.
Yeah, as we read A's, we're staying either in Q0 or in Q1. And we are staying where we were. I guess from Q0 we moved to Q1, and from Q1 we stay in Q1. We read a bunch of A's, and we push a bunch of 1s to the stack. What happens when we read our first B? Where do we go? We go to Q2. That tells us we are done reading A's. So staying in Q1 says that we are in the process of reading A's and adding 1s to the stack for each A that we see. Once we see our first B, we're going to transition from Q1 to Q2. Starting in Q2, we are going to remove the 1s that we added from the stack. And eventually, we can move to this accepting state if and only if, at the very end of this, we make no read from the input string, and we can pop a 0, that 0 that is the bottom of stack character. So if we're visualizing this as a stack, we start with a 0 on the stack, representing that bottom of stack character. As soon as we read our first character, it has to be an A in order to transition from Q0. Either we can immediately transition to a Q3 and accept, but we do that only if we're at the end of the string. I guess at this point, I should have mentioned the 3 necessary acceptance criteria for an NPDA. You must be 1. At the end of the input. If you're not at the end of the input, doesn't matter where you are, you can't accept. 2, you must have an empty stack. And then 3, you must be in a final state. If you do not have all 3 of these criteria met, we cannot accept. But since it's non-deterministic, there just has to be one such path. Just like with NFAs. There could have been 100 possible paths through the NFA, but as long as one of them reaches a final state at the end of the input, we accept. But now, instead of just being at the end of the input with a final state, we also must have an empty stack. So this last transition is getting rid of that bottom of stack character, so that we actually have an empty stack when we accept. But in order to make that transition to the final state, we must be popping that bottom of stack character. That means if there's anything else on the stack, we have to remove that from the stack before we can remove the bottom of stack character and accept. So starting in Q0, there are two things we can do from Q0. We can either immediately go to the final state and remove this bottom of stack character. That tells us that we accept the empty string. So this represents a to the n, b to the n, that same language we were just talking about. And a to the n, b to the n when n equals 0 is the empty string. So we need some way to teleport to the final state and accept. If n is not 0, then we need to read some number of a's and then that exact number of b's. Remember that this wasn't possible in a finite state machine. We drew out kind of how the states were going to next to each other, expand, 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 and eventually we would move and read the same number of b's moving backwards. But we found that the memory we needed for that state machine kept growing and growing and growing to represent and recognize larger n. Here from Q0, we just go to Q1. When we do that, we pop the 0, push it back, and push a 1 on top of it. This is the equivalent of just pushing a 1. But since we need to adhere to this formula, this type of input, we always pop something. You can pop nothing and then push something. But as we will see, that creates some issues when we talk about deterministic pushdown automata. So at the moment, my recommendation is pop a character, push it back. So this tells us that we read an A when we do it. So this stack now represents we've seen an A. And in fact, the number of ones on the stack will represent the number of A's that we have seen. From Q1, we can move back to Q1, popping a 1 and pushing 2 ones. The difference there being 1, 1. We pop 1, we push 2. The difference is basically we pushed 1. So we do that. We would stay in Q1. And we can stay in Q1 as long as we want reading extra A's. For each 1 that we put on the stack, that represents an extra A that we read from the input. And eventually, we run into our first B. When we run into our first B, we transition from Q1 to Q2 and pop a 1 off the stack. We pop a 1 and push nothing, which is the equivalent of removing 1. Then we can stay in Q2 as long as we want, reading extra B's and popping 1s. Note that if at any point there's a 1 on the stack and we see an A, there's no transition defined for that from state Q2, so we would immediately reject. We have to see legal transition as defined by these transitions. So we continue that process until we see a bottom of stack character. Once we have popped enough of these and seen enough B's, we will have revealed back the bottom of stack character, and then we can freely transition to our accepting state Q3 from there, reading no input and popping that bottom of stack symbol. As we do that, now there are no further transitions defined at Q3. So we must be at the end of the input in order to accept. If there are additional A's and or B's at that point at the end of the string, we immediately reject, even though we have an empty stack and we're in a final state. We have to be at the end of the input as well. Questions on kind of a walkthrough of how to read these transitions and what they mean with regards to the stack manipulations that we're doing? Maybe a show of thumbs for that, for this particular problem, reading this transition, understanding what this is doing. Seems to make a reasonable amount of sense. Not perfect yet, but reasonable amount of sense. That tells me we can look at the next thing. Here's a visualizer. This helps us to visualize what this is doing. So just like before, we're going to define an initial state Q0. Like we have up there, it tells us the initial state is Q0 in our text. Each transition now has those three characteristics. It's a three tuple of three elements. We're going to, on read an A, pop a 0, push a 1, 0, and that is a transition from Q0 to Q1. So that's just reading this and turning that into a visual representation. From Q1, there are two transitions defined as an outgoing edge. We can either read an A, pop a 1, push a 1, 1. We can read a B, pop a 1, push nothing. So all of the A reading is happening in Q1. We read a bunch of A's until we read our first B. So once we're in Q2, we can now loop through, read all of the B's, pop all of the 1s off the stack, and then transition on the bottom of stack character, reading nothing from the input and pushing nothing back to the stack once you've popped that bottom of stack character. So once we hit our final state Q3, we must have made it to the end of the input in order to accept, because we know where we've emptied the stack. By removing the bottom of stack symbol, we know we are at the bottom of stack. We know we're in a final state. It's the only final state, so the only consideration is, are we at the end of the input? Is this a thing? I don't think this was a thing.
No, it's on there.
It's on there. Q0 to Q3 on a lambda. Yeah, we are pop. This is just the popping of 0. This is the no case, and this is the read nothing but read an A. Yeah, it is weird. So I guess we accept a single A. All right. Questions on the visualizer? Visualizing it like we did the NFA back in the regular language land, it's just a little bit more complicated. Just like we did before, we can have instantaneous description format for things. So as we can see, transition graphs are super useful for visualizing regular language automata, but less useful for visualizing context-free language. It is a nice visualizer, but keeping track of three things on a transition is a little bit more challenging to represent and a little bit more challenging to read in general. So we're going to use an instantaneous description format to potentially read this as well. So here's another way that we can track a path through a PDA. So it's going to be, for each of these, there's going to be a triple again, Q, W, and U. Q tells us the state of the control unit, just which state we are in. W is now the entirety of just the unread portion of the string. We don't care about what we have read, but we care about what we have left to read. And then U is the contents of the stack, the entirety of the stack at the moment. And now we can see that a move from one instantaneous description to another will represent one transition, one of the legal transitions that we could take. And it tells us everything that we would need to know about what happened in that transition. So the transition character now is this turnstile symbol. It's useful in discrete to be able to say, it is provable that we can reach the destination from where we came from. Even though we used 0 to represent the bottom of stack symbol on the last example, for the rest of this quarter, we are basically going to use Z as the bottom of stack symbol. And that's just to avoid confusion. Oftentimes, if we're looking at a binary language for a stack, we will be using both 0 and 1. So we don't want the ambiguity of, is a 0 an actual stack character or is it the bottom of stack character? So Z is not particularly useful for anything else. So we will just use Z to represent the bottom of stack character. All right, let's go ahead and construct an NPDA. Here's a language. It's very similar to the A to the N, B to the N, but now we are not restricting the order that the symbols come in. We care about the number of A's being equal to the number of B's in the string. So as you're getting started with this, think first algorithmically, instantiating a stack, and then writing a program to solve this. How would you do it? I think that would help. And let's get started from here. You can either write this out as a sequence of transitions, or you can write this out as an actual automata diagram with states and arrows, whichever one works best for you. Thoughts on how many stack characters we're going to need to represent this? First question I might have when designing this, what do the stack characters represent? They usually represent an idea of some kind. On the last NPDA, in that last example, the ones represented how many more A's we had seen than B's, and we forced that order if all the A's come before all the B's. So each one that we added represented some number of future B's that we need to see in order to reach an equilibrium state, where we've seen the same number of A's as B's. So with that in mind, how many stack characters do we need for this problem? We need two. Why do we need two instead of one?
What is a stack character?
It's what can go on the stack.
So,
So aside from the bottom of stack character, which is not a stack character,
so 1 and 0, right?
we could use a 1, 0. What would they represent?
Well, I don't know, I was thinking originally maybe that, I don't know if we can have two different paths in a PDA, but if, for example, they accept a 1 as an A, then we keep that trend. If we accept a B as a 1 for the first character, then we keep that trend,
Okay,
but I'm not.
it's an interesting idea. How would we know at the end that we've seen, like, so for instance, they can cross. We could see some A's, like imagine the string AA, BB, BB, AA. At some point, we'd seen more A's than B's, and at some point, we'd seen more B's than A's. That's what our two stack characters are going to represent. How many more A's than B's have we seen? How many more B's than A's have we seen? And at each character in the input, we need some read on that. How many more A's do we need until we reach that equilibrium? How many more B's do we need until we reach that equilibrium point? And the different stack symbols represent whether we've seen more A's than B's or more B's than A's. Well, I'm being especially complete here. And then I'm pushing the bottom of stack character on as the very first thing that I'm doing. I'm not anticipating that that bottom of stack character is already on the stack. Depending on, this is where notationally things get a little bit gray. Either in your official definition, you say what the bottom of stack character is, like we had in our very first example. If that's the case, then you don't need to push it on. But if you don't dictate in some way what your bottom of stack character is, then it needs to be incorporated in your state machine in some capacity. So I am pushing on the bottom of stack character here, and then I am reading the first character here. So if the first character that we read is an A, I will pop the bottom of stack character, push it back on, and push an additional 0 on top of it. This 0 represents that we have seen, since there is 1 0 on the stack, one more A than B. If we see a B with the bottom of stack character, then we're going to replace the bottom of stack character with itself, and then push an additional 1. That tells me that we've seen one more B than A. The number of zeros on the stack, more A's than B's. The number of 1s on the stack, more B's than A's. Now we get to the fun part. This is where we're going to see just how ugly NPDAs are. Oftentimes in one state, we just have a south edge and a bunch of possible transitions on that south edge. So here, I'm going to do everything that I could possibly see on an A. Here, I'm going to do what I can possibly see on a B. And we'll see that there's a good bit. So if we read an A from here, it is possible that we're in 3 different cases. We could read an A, and from here, we could have a 0 on the stack. If there is a 0 on the stack, we want to add an extra 0 because a 0 says that we've seen more A's than B's. When we read an A, when we've seen more A's than B's, we've seen one more A than B than we did before we read the 0, or before we read the A in the string and saw the 0 on the top of the stack. So we're going to push 2 zeros, saying the difference between that is 1. We've now seen one more A than B. It's possible that we see a 1 on top of the stack, which tells us that we've seen more B's than A's. When we read an A and we've seen more B's than A's, we've now seen 1 fewer B's than A's than we had before we read this A. So we should just pop the 1. Do nothing further. And the other option is that we've seen an equal number of A's and B's, so the bottom of stack character is on the stack, in which case we should do exactly what we did coming into this, which is throw a 0 on top of the bottom of stack character. This is going to be mirrored and inverted for the B's. We read a B and there's a 0 on the stack, that means we've seen more A's than B's. When we read a B and we've seen more A's than B's, we've now seen 1 fewer A's than B's than we had before we read the B. So we should pop the 0. If there's a 1 on the stack, it means we've seen more B's than A's. When we read this B, we've now seen 1 more B's than A's than we had before we read this B. And if there's the bottom of stack character, then we should push a 1 on top of it. In order to move from Q2 to another state, we need to now have the bottom of stack character, and then we need to remove it. So we are going to have a single transition out of here on the bottom of stack character. We read nothing from the input. We will see that there is we're gonna pop a Z and push nothing. And that gets us to a final state, Q3, that we can accept from. And we only will be interested in taking that transition if we are at the end of the input. Note that since this is non-deterministic, we will frequently be doing multiple of these transitions at the same time, but we only reach acceptance on a thread if we are at the end of the input. So frequently we will find ourselves in Q3, but there are still input symbols to read, therefore there's no reason. Unfortunately, we are out of time, so we'll have to come back to this tomorrow. But hopefully this is starting to make a little bit of sense, at least in terms of seeing a solution to this and understanding why it works. If not, feel free to swing by office hours. I'd be happy to explain it in more detail. Bye. Office hours starting now for any homework assistance or class part 2 from today.